Like using the parameters how to overlap the computation, for example, waiting for a so these are more implementation of how yeah, yeah.
Like just a very literally that's what
Yes. whether we are gonna have like.
Welcome, everyone. We have a very exciting lecture for you today. We will discuss for the first time function approximation reinforcement learning. We get rid of tabular and table assumptions. The assumption that we know all the states of the environment and they're listed in the table ahead of us. So you can say that starting from today, we can have the first realistic setup where you can really, deploy a reinforcement learning method and learn a policy in an environment where you have where the environment emits some external reward. Okay. So let me just recap what we have been trying to do since the beginning of the course so far. We started with tabular methods where we said that we have a finite set of states, which we know, and we also have a finite set of actions, okay? And we knew the dynamics and we knew the reward function, and our goal was twofold. First, if I give you a policy, I want you to compute the value functions and the action value and the state action value functions. So we call this policy evaluation. And the second was the control problem. How can you learn to act optimally in that MDP? And we put down two solutions. We said that, first of all, for the policy evaluation, we can solve essentially the Bellman expectation equations. It's just a linear system of equations, but this is too costly. So then we also propose some iterative way of computing those value functions, V pi of the policy pi. Then in the next lecture, essentially, we got rid of the assumption of knowing the dynamics and the reward function. And we said now, instead of having an agent sitting in front of his laptop and trying to do computations, okay, to essentially compute the state value function, the state action value function, now we have an agent that actually interacts with the environment and collects trajectories. And we said that trajectories are sequence of state action rewards, which we'll use directly for the same two problems that we had before, policy evaluation and control. Okay? Policy evaluation is I give you a policy and you need to compute the state value function, state action value function, and control is coming up with an optimal policy for that MDP by interacting with the environment. Now, in the case where we got rid of the assumption of knowing the dynamics and rewards, the Q, state action value function, becomes very, very important because it is essential if you want to learn control, if you want to essentially improve your policy and iterate essentially between evaluation and policy improvement to find an optimal policy for your MDP. So that's why we pushed aside a little bit the V pi's and we focused on estimating Q pi's from experience. Okay, because we said if I know the Q pi, then I can obtain a better policy directly simply by acting greedily with respect to the estimated Q. Okay, right? While before, when we knew the dynamics, we would estimate our V pi's. From the V pi's, we would use the dynamics to estimate our Q pi's and then again go ahead with our policy greedification. All right, and so then essentially we describe these different versions of this method called policy iteration, which is the alteration between policy evaluation and policy improvement. And we focus on two ways of doing that from agent's experience. One, we called it Monte Carlo, and the other, we called it temporal difference learning. And both of those, we saw that they're just approximation, okay, of the Bellman equations. It's just different approximations. One using bootstrap, using the current value estimates, and the other doesn't use. It just uses the sum of rewards from each state till the end of the trajectory, okay, to estimate this value functions, the state action value functions. And so this is what we did. In both cases, we essentially put down control algorithms, all right, that would allow you in a tabular setup to come up with optimal policies for that setup under the assumption that you keep visiting every state and action many times. To do that, we said that it's very important, the policy that is deployed in the environment to be exploratory, okay? And to be exploratory, for sure, you cannot be deterministic because otherwise for every state, you will always place the same action and you will never get the opportunity to estimate advantages of the other actions. Advantages means the Qs of those other actions, and the advantage is essentially the difference between the Q of that state and action over, the V of the current state, right? How much you would gain if for every state S you would switch to that action A instead of the action that your policy is doing right now, okay? We talked about this in the gratification process. And last lecture specifically, we again went back a little bit to assuming that we know dynamics and rewards, and we discussed about online planning, okay? How I focus on a particular state of the environment where I know I need to play, I need to act, and focus all my resources on look-ahead search from that state onwards. And I know I can do look-ahead search because I know the dynamics, which means I can come up with actions in my head and feeding them into my dynamics function. And my dynamics function will give me essentially possible next states with the probability of occurrence. That's exactly the transition function. And we said how to use this essentially transition dynamics in Monte Carlo tree search, okay? An online planning method where the actions that you evaluate mentally in your head improves over time, right? So you just sit there, the opponent is waiting, and you just sample action sequences. You see the results mentally. You see, did I win? Did I lose? You go and update, compute queues for the states and actions that you actually visit. Then update your policy using the UCB criterion. If you remember, this is the policy that you have. We call this, tree policy. Essentially, outside of the tree, we're still playing randomly. And you keep playing better and better and better till, your time is up. And you really need to spit out an action for this particular state that is the root of your tree, okay? Then you play that action. The opponent also thinks and plays something. And then again, you start planning. And instead of starting from scratch, you may as well start from the tree that hangs below the actual next state from your previous mental tree. And then you keep expanding, keep playing, etc., etc. And we show the method like Monte Carlo tree search so that the actions you evaluate mentally become better and better over time. Do you agree with this summary so far? Okay. Do you have any questions? Like, I do believe that the first chapters are extremely confusing. That's why quiz 1 is early on, so that you are tested and, kind of spend time reading those. Make sure you classify them in your mind. Now, the good thing about the first third of the course is that we have a book that is extremely well written. So you can take advantage of the book, because later this is not going to be the case. We're just going to be, mostly relying on papers. And, papers are not as clearly written and do not make connections. First of all, every paper has a different author. So this already creates problems. Okay. So I really encourage you to go and check the first chapters of the book. By the way, the website has been updated. Critical missing was the chapter 8.11 that you were supposed to read for last Wednesday for the Monte Carlo tree search. I mean, today, again, we're going to talk about Monte Carlo search, so please go ahead and read it today. It's a small sub-chapter of the book, okay? And here is where we are today, where we're going to get rid of tables, we're going to get rid of tabular methods, and we're going to essentially compute state value functions, the state action value functions directly from sensory representations of the state. And we'll discuss why this is very important. Okay, so tabular methods, the way we have described them so far, we cannot use them in any real world problem, simply because enumerating all states is just infeasible. The states are just too many to enumerate. Okay, it's as simple as that. So that's why we resort to value function, what we're going to call value function approximation. What does this mean? It means that so there are too many states, but the most important thing is, I'm not going to visit all those states at training time. At test time, new states are going to show up for which I will have zero clue what to do. Okay, so you really, if you want to really act and behave in the real world, you need to be able to generalize from similar states to novel states that show up, that, they're not completely novel, that you have no clue, but you can, transfer information, transfer knowledge from states that you have seen before. And the better your representations are, the better such transfer of knowledge, the better you can generalize and essentially show competent behavior in novel environments. okay, and novel states of the same environment. So here is how things are going to look like. Instead of our value functions being tables, where every state is a different row, and for which we need to compute a scalar, now our value functions are actual functions. They're parameterized functions that depend on some parameters W that we're going to estimate, okay? And here is the big difference. In previous chapters, when the value of a particular state was updated, right? If you remember, V of S new equals V of S old plus alpha a tiny little positive scalar, the target minus the V of S old, right? So each time we would update the value of capital V or state action value of a particular state action pair, no other pair was affected. Do you see? So we would go and update every state or every state and action independently of any other one. Now that our state values and state action values are functions, each time we update W, the values of all states and the values of all state actions are updated jointly. Okay? Do you see? So there is now an interdependence between states as well as state and actions. And this has good and bad. First of all, we need this interdependence, otherwise we cannot transfer essentially knowledge. But at the same time, we need to take care of interference problems that cause, let's say, stability issues during training of those state action value functions. Does this make sense? Okay, great. So here is how the V's and V hat and Q hat, because these are estimates, these are what we used to call capital V and capital Q. This is how they look like. It's a parameterized function, and the input is a representation of the state, or a representation of the state and a representation of the action. Okay? Now, in our case, where we have, so far we've seen only discrete set of actions, there also will be a second representation for Q, where the state representation comes in, and then as output, you have the Q of every of your actions in your small discrete set. And the important thing to remember is that the length of this parameter vector is much, much, much smaller than the number of states in the environment. Okay, so before we had to learn scalars for every single state. Now we need to compute the parameter. We need to compute every single parameter, but these parameters are much, much less than number of states, and all these parameters are shared across different states. Okay. And this is when we update the parameters W, the value of many states or many state and actions change simultaneously. And the same approximation we'll also use for policies, in which case a state representation comes in and the output will be a probability over or a discrete set of actions. So typically when we have discrete actions, the last the last layer of that policy, let's say function, is a softmax, which we'll visit in detail. Essentially, we have logits, preference for every action, which we raise in the exponent, and then we divide with sum of exponentials. And in this way, essentially what we compute for every action sums to 1. So it's a probability that our policy network assigns to each of different actions. And though many parametric and non-parametric functions can be used, we are going to focus on parametric functions and specifically in neural networks. Okay, and why? Well, because learning is easy with let's say gradient descent. So how exactly is going to the estimation problem is going to look like? Well, first of all, we're going to put down an objective in just a few slides from now. All right, and then essentially we'll take the gradient of that objective. And because we're trying, typically, that objective is a loss, which means we're trying to minimize it, we'll be taking steps on the negative, towards the negative of that gradient vector. That's it. And there's going to be, so here's the step size, and there's going to be, again, a parameter alpha, which is not by accident the same symbol as our previous alpha, is the learning rate, how fast we want to be updating those parameters, okay? The same as before, how fast we wanted to update our value functions. Okay, and in fact, we're going to have a whole lecture on that parameter alpha because it's very critical to compute it correctly for stability reasons. Okay, So what happens? Same as before, we would initialize, do you remember what we did in the previous 2 lectures ago? We would initialize randomly the values of all the states, right? Scalars for every state. So now we will initialize randomly the parameters of our functions. We just instantiate some random parameters, and then we start doing gradient descent. Now, because that gradient descent better converge and things should not go crazy, we're not going to come up with very big numbers for those weights. We're going to actually be using standard techniques from neural networks of how the weights are initialized in a way that training is facilitated and so on. So we're going to be using standard weight initializers in your, let's say, PyTorch or TensorFlow packages for this. Okay, it's just I want to show you the analog with the way we initialize the value functions. Okay, so let's so now that we know how we're going to be optimizing the objective with standard gradient descent, let's go and see what should that objective be. Okay, so again, we're going to discuss first of all policy evaluation, which means I give you a policy and you need to compute some estimate of the value function or the state action value function, either v hat or q hat. Is that clear so far? Very simple things, very intuitive things we're saying today. So let's see. So if we had, imagine we had access to the oracle, v pi of s, and that oracle for every state I would feed in, it will give me the correct, the true value of that state, correct? And now my goal would be to compute that function, v hat s comma w, that essentially will, predict the oracle values. Then this is just a standard regression problem, standard least squares. Does that make sense? Yes?
Is that v pi the same as v star? Is that pi optimal in space?
Great. So the question of your colleague is this v pi the same as v star, which is the value of the optimal policy? Is this what you're saying? Does anybody want to answer? Yes?
I think it is just the value function for the current policy v pi, and it does not necessarily need to be the optimal policy.
Right. I give you a policy pi, and I ask you compute the value function of that policy pi. And you know what? This is going to be a very important sub-process towards computing the optimal policy. We've done this before with Monte Carlo and with TD, right? We had the policy, we deployed, we compute the value function, we gridify, then we have a new policy, collect experience, again try to compute the value function. And so we're trying to do exactly that evaluation step of the policy iteration, right? So policy iteration is iteration between evaluation and gamification improvement. So now we're talking about that evaluation step. So the v pi is there for a good reason. That v is not the optimal, is for that particular policy pi. Okay. All right. So if we knew those oracle values, then we'll just do a regression. Do you guys agree? You kind of agree. Now here is a very subtle issue. As I have said, there are too many states. Okay. So the question is, which states do I need to show to my function approximation to estimate? Are all states weighted equally? Okay. That was the case when we had dynamic programming, right? For every state, we had to compute a scalar. Well, now we're approximating things. And when you approximate, you can make sure your function really works well under a particular part of the state space, and it can be crappy for a different part of the state space. You remember that we motivated reinforcement learning as essentially a specific approximation to dynamic programming, where we said not every state counts the same. The states that the agent visits actually are more important. And that's what expectation under policy pi means. It means that we have a particular policy that induces a state visitation distribution over the states. Some states are visited more by the policy and some states less. And essentially, I take into account that probability induced over states when I compute my regression problem. The states that the policy visits more, you need to, are essentially weighted more. All right. So it looks like that, as if you have a homologous sum over all states, and there is a weight for every state, which is the probability of essentially how much time the policy spends at a particular state. When the policy spends more time in a particular state, then that weight is higher. Okay. Is that clear? And it's true because, for example, yeah, so many times when you play chess, some board configurations, as we said, will never show up, will just never show up. So it doesn't matter if you don't know how to play from those configurations. Is that clear? Okay. By the way, this is very important. There's a very, very interesting paper from 1970s from Herbert Simon that is perception in chess, and to see how also human players are tuned on the states that actually show up as opposed to other states. So there, Herbert Simon, which was actually a CMU professor, showed that for the states that are frequent in chess, the chess masters, they could see this for milliseconds, and they can tell exactly where every, horse, where the horses were and where the queens were, while a person that doesn't know anything about chess, you show at the same time the board configuration, and it cannot tell anything about where the pieces are. Now, at the same time, you show to those chess masters board configurations that don't show much in chess, and they have no clue. Do you see? They cannot do the same guessing as the states that they actually see frequently. Which means what? That we're just very, very adaptive. Things that show up, we learn them well. Things that don't show up, we don't have a clue. Does this make sense? We don't value all chess board configurations the same. Is that clear? Okay. By the way, these are going to become a much more, intuitive once the methods show up. You will see that we have a method that actually visits some parts of the state space. We're going to be fitting those neural networks from the training data from that policy, of course, from this transition. So naturally, our approximation will be focused on the state and action that we actually visited. So we don't say anything very, non-intuitive here. Okay. Yeah, so this in contrast to just weighting all states the same. That's what is just to be clear, what's the contrast. Okay, so this is on policy state distribution. This is how we compute how much time a particular, let's say, policy spends at every state. The way to compute that is first you come up with this eta s, which are unnormalized, but follow essentially those recursions, right? It will show up also in later courses, later lectures. And at the end, you normalize, and then that's how you get your mu of s. Now, you don't need to worry at all about those mu of s. I'm just trying to explain how exactly the math works out. But now that you're going to go to do the approximation, you're going to see you're just going to be sampling from an experience buffer. So there is nothing to worry about. All right. So we have least squares. So what are we going to do? We're going to take the gradient over loss function, and then the delta w, which is the step size, essentially is the minus 1/2 simply to get rid of the square there, alpha, the learning rate, and the gradient of our objective. And because it's least squares, the gradient is what? 2 multiplied with a parenthesis and the gradient of inside the parenthesis. The gradient v pi of s is 0. V pi of s is constant. So the only thing that you are left is the gradient with respect to the parameters w of v hat. Is that clear? I just differentiated the square. Is this 100% clear? This is a standard regression. Okay, yes?
The importance of the states is also being updated with experience. Or is that something that's evaluated first and then used?
Very good question. So in this super non-realistic setup, which is just for demonstration purposes, because actually I don't have access to those oracle values, imagine that I had a policy and I deployed it for long enough time and I collected a bunch of trajectories, and these are now, that's essentially this induced my state visitation distribution. Okay?
So in this case, during the optimization, it would be just on the weights.
Yeah.
Not necessarily on the state important.
Exactly. Yes. Because the state is just fixed. We don't iterate yet. We said, okay, I have some states. I visit them with some frequency. I compute the data. I have for those states the oracle values. I just want to estimate my parameters W. And I'm just saying this is just a standard regression problem. And that's all. That's all the slide is saying. Okay. And you compute it with gradient descent. And you're going to start from a random W0. And that's it, pretty much. So this is just gradient descent. Now, you know that in neural networks, we usually do stochastic gradient descent, which means we're going to be sampling that step size. You have tons and tons and tons of training samples. You just sample some of them, fit them in your batch, and take a gradient step. That's all stochastic gradient descent means, okay? You don't consider all possible training samples at every time step to update your parameters W. Is that clear? So everybody knows that from intro to ML, okay? Correct? All right. So stochastic gradient descent with experience replay. So now we reply to the question again of your colleague. Give an experience that consists of state value pairs. Okay, so I give you this experience ready, capital D. We're going to denote that experience buffer. And then what are you going to do? You're going to sample some state value from that experience, and then you're going to apply gradient descent. And this converges to the least square solution. Okay, so as you see, the experience is frozen, is given to you, and then you just update gradient descent to update your weights. Is that clear? Okay. All right, now nobody has access to the oracle. Nobody has access to the oracle. So what are we going to do? We're going to do the very natural thing of not using the oracle value, but using the targets. Which targets? The Monte Carlo targets and the TD targets that we saw in previous lecture. That's it. So now we can go back and revisit all our Monte Carlo policy evaluation, Monte Carlo control, but instead of directly updating the state action values, capital Q, if you remember, now we're updating that function Q and essentially the parameters of that function. Is that clear? Very simple. Okay. So wherever we had capital V, now we have V hat of the state and the parameter vector, as you see, okay? Okay, so let's go then and focus first in the Monte Carlo with the, value function approximation. We're going to have returns GT, which is an unbiased sample of the true value V pi, the oracle one that we don't know. So this means that we have deployed our policy and we collected some experience buffer that looks like that, like pairs of states paired with a corresponding return, which is the sum of rewards from that state onwards till the end of the trajectory. And that's how we're going to be updating our parameter vector. And it converges to a local optimum. We don't have now any guarantees of finding the global and so on now that we have function approximation. Okay. So here is the pseudocode from our book, exactly what you would expect. The input is the policy to be evaluated. We're talking about policy evaluation, subroutine. I have a differentiable function. I initialize the parameter weights theta, which we'll always call them either W or theta. The book uses both, I think. And you generate an episode, and either using that single episode or multiple episode, experience from multiple episodes, then you go and update your parameters theta. Now, a big hidden hyperparameter is how you interleave the experience collection with the parameters updates. Do you see? We'll talk about this in detail. This is very, very important. For example, how many trajectories do I need to collect before I go to update my parameters? Okay, that's one important question we need to answer. Can this be little? Can this be a lot? If it's a lot, then I take much time, right? I need to collect a lot of experience to update my parameters a little bit. If it's fast, maybe my estimation will diverge, and we're going to see those problems in a tiny bit. But so far, I think this makes total sense. This is just a regression problem. Any questions here? Yes. Okay. Like here?
The gradient update where you the next one. So we replaced P5 here with GT, right?
Yes.
So GT is also a function of V hat. So we are taking, which is also a function of W. So you're taking the gradient with respect to W. Shouldn't the gradient be taken with respect to GT also?
Yes. Okay. Very good question. So actually, this is even more pronounced here, right? Because GT, I agree, indirectly, because your trajectory is a function of your policy, right? So of course, the sum of returns for every state onwards depends on your policy, right? Because if the policy is crap, that return is going to be small. If the policy is awesome, the return is going to be large, okay? You're talking about this type of interdependence and how we do not take into account and use GT as a ground truth target to regress towards, correct? Look at the second case, which is even more crazy. Here, my target, which is immediate reward plus gamma and the V hat of the next state, actually, I see the W right there in the red target, all right? Did we differentiate through that or will we do that? No, we don't. That's why we call those semi-gradient methods. We pretend this is fixed and I just need to regress towards that. Do you see?
Is this also guaranteed to converge to the local minimum?
Very good. So let me tell you, in practice, this can lead to huge instabilities. In fact, the breakthrough paper in reinforcement learning of 2013, playing Atari games with human-level Atari game playing with neural networks, exactly solved that problem. He said, you know, this is the right way to update, but this creates instabilities. And here are two tricks, two solutions to actually make that estimation stable. And we'll visit those today. Does this make sense? But this is excellent, the question. Other questions? Yes?
Are there cases in which you would change the size of alpha throughout the
Yes, the alpha choice is extremely important, and we will see how to compute it in 1 or 2 lectures from now, two lectures from now. Yes, and the alpha is actually very important. Okay, let me give some more detailed answer. Even from supervised problems, so if you train an image classifier, the learning rate may change. In fact, they say learning rate schedule. There is a perfect schedule. In the beginning, the learning rate typically is larger, and then as you go on, it becomes smaller and smaller. And in fact, the learning rate schedule is exactly what Jeff Hinton and his students sold to Google when at 2012. It's like, oh, we're going to give everything to the community and the neural network model, but the learning rate schedule is just going to be sold to Google. Do you see? Now, the truth is that this is case for supervised learning, where the targets don't change, meaning every image has a label, and this doesn't change as your classifier keeps training. Now, in our case, things are much, much harder because as the policy changes, the data change. Because the policy changes, visits different parts of the environment, it selects different actions and so on. So if you make a mistake and your policy becomes worse, then your data look worse, then the next policy also is worse, and so on and so forth. Does this make sense? So, so the reinforcement learning method is much more sensitive on that alpha parameter. Okay, and we're going to discuss about what we call natural policy gradients, where essentially we'll see how we can, depending on what your policy is, how you can essentially compute your learning rate. Concretely speaking, you try not to change your policy too much. Do you see what I mean? You take gradient descent steps, and essentially you make sure that you don't change the probability of the actions at every state of from your training set. They don't change too much. If they change too much, then you backtrack. Does this make sense? You don't want your policy to change arbitrarily much from one gradient step to the next. Is that clear? Yes.
So, like trying to make sure that future time sets the data is IID as really set.
Yeah, so there is no way the data will be IID because over time, so look, this is a trajectory you're going to be collecting. It's all in the very nearby locations of the same amphitheater. They're insanely correlated, okay? But you're raising a very good question. We know that to train neural networks, you need decorrelated samples. So how we're going to actually take gradients here if all the training data comes from the same trajectory? Is this what you're asking? Excellent. We're going to reply. This was exactly one of the 2 contributions of that paper that I just mentioned earlier. Okay? Yes.
If you sample randomly from the experience replay, doesn't it like kind of fix that?
Yes.
It's not dependent on the time.
Excellent. So your colleague suggests now the first fix, which is not that you collect one trajectory, you're going to feed it in your update. You're just going to collect a lot of experience. Okay, and during that collection of experience, the agent may manage to go up and outside from the amphitheater, and in this way has more decorrelated experience, and then you sample from that experience buffer and you make your batch. Other extremely important to fix is the following. Instead of having one agent, exploring here in the amphitheater, have other agents in other places of the CMU campus, and you in this way, you ensure that different agents essentially collect experience that's not correlated, and they all contribute training examples, and in this way, your batches are indeed decorrelated, and gradient descent on the neural network works. Is that clear? Okay. Other questions? Okay, so here is value function approximation with TD, exactly the same thing. And here is the amazing thing, exactly what your colleague said, we'll ignore the dependence of the target on W. Let's forget about it. We'll treat it as if it's a constant. So this is called the semi-gradient method. And here is the corresponding pseudocode, much like the MC pseudocode, but instead of GT here, you have immediate reward observed plus gamma V hat of the next state and so on. And we said that this is a very naive pseudocode. This is not the pseudocode we're going to be following. We just discussed about the problems of correlated training data and so on. So just hold for a few slides to see exactly what is the right way to do things, okay? Okay, so this is policy evaluation. Policy evaluation. Now for control, you're going to do two things, right? So for control, we do two things. Policy iteration, which means what? What is policy iteration? Policy evaluation, where we're going to approximate the Q pi, okay, the state action value function from the present policy, and then policy improvement, which is what? Epsilon gradification with respect to the estimated Q. That's it. All right. If you remember, this was a policy iteration. This is a standard control. So now we just discussed about policy evaluation. So we'll form exactly the same thing, but instead of V hat, we're going to use Q hat. That's it. Nothing else changes. It's still a regression problem. You can still take a gradient. The delta W, which is the step, is very, very similar. It's essentially identical. And you're going to have two different targets, either the Monte Carlo target, which is the return, which is the sum of rewards from that state and action that shows up in the trajectory till the end of the trajectory, or the TD target, which is immediate reward plus gamma Q of the next state and action. All right. This is essentially the deep SARSA version. Do you remember SARSA? You remember that we said last time that this is how we call it? Yeah. So in any case, these are exactly the same things, but instead of V hat, we just applied on Q hat. And so let's see. Yeah. All right, so let's see the full control method now, because SARSA is, let's say, TD control, on policy TD control. So not only policy evaluation, not only finding the Q, but also gridifying the policy. If you remember in SARSA, we have an epsilon greedy policy that we use both to collect experience as well as to compute the Q function. That's it. So we'll start, we initialize the parameters of that Q hat randomly, all right, arbitrarily, and then we deploy the policy and we collect trajectories, and we are updating the Q hats, and then we choose alphas as a function of the Q hat using the epsilon greedy scheme, all right? And essentially what means epsilon greedy? Each time your Q is updated, then your action selection changes, because the action selection is just epsilon greedy of the resulting estimated Q hat. Okay, so this is deep SARSA. Okay, so that's it. Much like prediction, but now the targets for the Q pi. So we have the GT, we have the GT is the target for the Q hat, and then immediate reward plus gamma Q of the next state and action is for SARSA. And does anybody want to guess what is the deep Q learning update rule? What was the difference in the Q learning in the tabular version with respect to tabular SARSA?
There was a max of
There was a max operation. Is this also what you wanted to say? Yes. The max over what?
The target.
Okay. Great. Very good. So the max over all the actions on the next time step. So you don't fit there the action that you actually took. You take the maximum across all actions. And you can estimate those because you have the Q hats of those. Okay. So I know what is the Q hat of the next state and every action I plug in there, not just the action that I actually took on the trajectory. Is that clear? Yes.
Just a clarification. So only for AT is it taken from the episode data? I'm just confused that the actions being used in the queue, is that something that we sample from available actions, or is that what we take from experience data?
Okay, great. So here's it. So here capital S and capital alphas are all random variables. So now your question is, what do I feed there? What I'm going to be feeding in those placeholders, correct? They're precisely the state and actions that show up on your trajectories, okay? So you take your trajectory, which will have some S0, alpha 0, R0, S1, A1, R1, and so on, which is the actual states, action, rewards, action, state, action, rewards, and you just plug them into those equations.
So in the previous slide,
in the previous slide.
When you said take action from
here,
choose A prime as a function of Q, example.
Yeah.
Is that being taken from the trajectory, or is that something that we like select?
So it is exactly the same. You sample that action, okay, A star, you go and update, and you deploy it on the environment. Look, action now becomes A star, and you go and say, take action A, observe RS prime. Do you see what I mean?
So we're also changing.
So essentially, we sample an action. First, we apply it on the environment. I see the resulting state and reward. I go and I form my update. That's it. Is that clear? So the same action that I sample, the same one action I deploy in the environment, then I see the next state and reward. There is no other way I can see the next state and reward because I don't have the dynamics function. I really need to deploy an action in the environment to see the resulting state and reward, correct?
So we're collecting trajectory data live?
Yes, live. Very good question. So you collect the tuples of the form state, action, next state, reward, next action, and you feed them there in your algorithm. Yes, you collect the trajectory data live. Now, there is something else we're going to discuss just now, which is you don't need to be collecting, a trajectory segment and then going up and update your parameters. In fact, this will not work because of the correlated samples. You can just collect for a very long time, and then just relax, stop collecting, or have one agent to keep collecting and the other agent, CPU agent, to be computing and updating the parameters. Does this make sense? But in both cases, the states and actions that are going to show up in your equations are state and actions from your trajectory data. There's no other way you can know which is the ST plus one for a particular ST. It's just the ST that showed up in your trajectory. Is this 100% clear?
Yeah.
Okay, this is very, very good question, very important. All right. There's no other way we will know anything about state sequence over time beyond our trajectory data because we don't know the dynamics. Is that clear? Okay. Other questions? Okay, so now we'll go back and look closer to the comment of your colleague about how do we interleave trajectory collection and parameter estimation, okay? Update of the parameters theta. So we'll visit that very nice paper. It's called Deep Q Networks. It is in the required reading of today's course. So we essentially will be we're going to use in the Deep Q learning rule. We saw in the first slides that for the Q function, you have a neural network that takes as input the state representation and the action representation. When you have discrete actions, which is the case in today's lecture, that would be preferred. Why would that would be preferred? Let's say, and keep in mind the deep learning update rule, okay? That for a particular state and action, essentially needs to compute the maximum across all actions of the next type step, okay? Why that representation of the state action value function is cheaper, is computationally cheaper, because I can fit the state and get the queues of all actions at once. While if I didn't have that, then I had to, do a forward pass on my network for every single action on my discrete action set. Very simple reason, okay? Okay. So now we all keep in mind about that Q function that takes as input the state representation and spits out scalar values for different discrete actions. And let's go and do what we just learned. We're going to taking immediate rewards and gamma max across all actions of the Q next state and next action. Well, unfortunately, the max needs to be across A prime, not across A, okay? Minus the current Q of S comma alpha. And this indeed converges to the true Q star when we have the table local representation. This is what we discussed in the previous lecture when we talked about tabular Q learning. This indeed converged. Now, the truth is that if you try to do exactly the same with neural networks, with functional approximation, things don't converge. Why? For two reasons, which you guys have hinted on both of them. So the first is the fact that what your colleague said, that the target changes over time. So the target essentially is non-stationary, right? Okay. Because as you train your network, the queue of the next state and action also changes. All right. So you are essentially chasing your tail, and essentially this causes the gradient descent to diverge. And the second is again something that you guys hinted, which is the correlation of the training samples. All right. If you just take a trajectory, all states along that trajectory are going to look very similar. For example, gray carpet, person with red t-shirt. Do you see? So they all look very, very similar. So this is not what you want. You want decorrelated samples. So now here is the paper that you guys need to read for today that actually presented two extremely simple, fixes to these two problems. And is the first paper that manages to train reinforcement learning methods directly from pixels. This is the main, let's say, contribution of that paper. And it's extremely, seminal paper, which also give, let's say, I think after that paper, DeepMind was formed as a sub-company inside Google and so on, and it was bought by Google, etc. So very intuitive solutions to those basic problems. So, okay, we're ready now to see the fixes. So the first fix is we need to remove correlations between samples. So then we go back to your question of your colleague. Do we live collect the data? And they say no, just you have a particular policy, deploy the agent in the environment, make sure you collect a lot of trajectories and throw all of them into an experience buffer in the form of state action reward next state. That's the only tuples you need to form the deep Q learning update rule. So while the trajectory may be very, very long sequences, you just chop them into state action reward next state. Is that clear? And then essentially you will be sampling those tuples and feeding them in your equations and then forming gradients and updating the parameters of your network. Okay, so I think the paper says, collect 1 million samples. And once you collect 1 million samples, start sampling from your experience buffer and updating your network. Okay. And new samples, then deploy again the agent, collect new samples, throw them in the experience buffer, and throw away the older transitions. Yes.
I'm just curious. You mentioned that this paper was published in 2013. How long did it take the RL community to figure this out? Like how many years passed?
To figure out what?
That they needed to do this, like remove the correlations.
Yeah, well, not much, right? Because in 2012, is when, image classification with deep neural network showed up. And so right the next year is like, you know what? Now we have deep nets, we have GPUs, make sure you decorrelate the targets. And so it didn't take that long. All right. Yeah. Other questions? All right, so now we have decorrelated targets, but we haven't solved the other problem, which is what? Yeah, non-stationary targets. Now, here's what we're going to do. We are not going to be using the same. Yeah, so all the subscripts under max need to be A prime. So I'll fix this typo in the slides, okay? Now, we're not going to be using the same parameters W to form both the targets and to also update. We're going to have two separate networks, all right? Two separate Ws, W minus and W. W minus is going to be used to form targets for W. And W minus will be held constant for some number of iterations. And after some number of iterations, then W will be copied with weights of W. Does this make sense? So then, essentially, W can make some progress towards some W minus, all right? So essentially, you can have some, healthy gradient descent to a particular set of targets Q max across alpha QS prime A prime under W minus. And once the neural network, made some progress and converged on those targets, then you form new targets using by W minus essentially equals W and then repeating the same thing. Is that clear? And how many iterations you need to wait to update the network is a hyperparameter. They give this in the paper, and many other choices potentially would work. Okay, does it make sense? Yeah, so these are the two fixes, guys. That's all that you need to do. And now you can, put a lot of GPUs and train Atari game to play Atari games directly from images. Okay. Right. So what is experience replay? Experience replay is that you can use a particular tuple multiple times. All right. This is standard thing in when you train networks. The same example is essentially used multiple times to update the parameters, not just use once and then you throw it away. And the same thing we're going to use. Here in DeepQ learning. All right. They use experience replay. They have specific Q targets. You store transitions of the form, state, action, reward, next state, okay, in the replay memory. You sample some random mini batch of those transitions from the experience buffer D, and then you compute the Q learning targets with respect to the old fixed parameters W minus, and then you optimize essentially mean square error between the Q network predictions here, QS, alpha, WI, and the Q learning targets that are given by your WI minus, all right? And now it's simple to note the iterations of the learning process. So this is the Q learning target, and this is the Q network, okay? And we use stochastic gradient descent. That's all the recipe you need to train those networks. And I think a homework 2 will have you to train this type of networks. Is that clear? Yes?
I imagine in practice, you can't keep storing new experiences because you blow up in terms of space and new experiences.
Yeah.
How important policy used to replace the old experiences? What policies are generally?
Right. So usually you have a replay buffer that has, let's say, a fixed capacity, let's say 1 million tuples. And as new experience comes, the older tuples are washed off.
This is first and first. It's not based on like the last sampled one. So if you've sampled some experiences in the past from the buffer, it's not like you give them more priority, like what?
Yeah, good question. So great. So there's something else that we're going to see. It's called prioritized experience replay, which means the following. Every tuple in your experience buffer comes with a particular priority. And that priority depends on the, let's say I'm a tuple. I'm the tuple S alpha next state, and next alpha doesn't matter because in any case you take max, okay? And you compute the difference between the estimate of your Q network for that state and action and what is the target. So if the difference is large, you need to give priority. Why? Because if you use me to take gradients, it doesn't mean that after gradient step, that error is going to go to 0. Why? Because there is a tiny little learning rate alpha. Each time you make those errors smaller and smaller and smaller. Do you see what I mean? So potentially, if a particular tuple gives you a big error, do you understand what is the error here, guys? The difference between the target and your current estimate from your Q network. That's called the error. It's called the TD error, okay? So if a particular tuple gives you a big error, a time step T of the training process is also going to give you a big error the next time this tuple shows up. Does this make sense? And as you keep seeing the tuple, eventually that error will go down, let's say, in some healthy training, let's say, instantiation. All right, so the prioritization of the tuples depends on this error. Now, to compute the error, you need to use the tuple once to feed in your network, all right? Okay. All right, so this is how deep Q learning works. We have Atari, and then we have a Q value function that computes values for every state and action. And we have a joystick that has 18 different actions, and we have rewards. And there is an important GPU there that, or whatever. No, this is the environment. And a very, very important question is, okay, what exactly is the architecture of that Q network? And the architecture here is pretty straightforward in the sense that you concatenate 4 frames and you get a bunch of convolutions, and at some point there are some fully connected layers, and this gives you the final logits of those 18 actions, and then there is a softmax. No, actually there's no softmax because it's a Q network. And essentially you just have a fully connected layer that gives you the values of the different, all your 18 actions. All right, so very straightforward architecture. Of course, you're going to use some convolutions because you have images as input. All right, and in this course, we're going to see different architecture, different backbones, both for policies as well as for value functions. And you will see, guys, that this is very important choice because depending on the backbone, you have different guarantees of or hopes for generalization of your policy and value to novel environments and so on and so forth. Is that clear? For example, just to be clear between us, if you train here your policy or your Q value, because this is deep Q learning, under this type of images, once I take the black background and make it white, your value function is going to fail. It's going to spit out garbage. Is that clear? So it's not like you guys that you are excellent, perceptual agents, and you can very easily generalize across variations, and the master looks a little bit different and moves slightly different, and you can still very fast adapt. This is not the case yet for machine learning or deep learning models, because the inductive biases of what that value function needs to look like or what that pose needs to look like have not been figured out. But there are very important steps towards that direction year by year. Is that clear? Okay. All right. So some direct extensions. The second one, in fact, we already discussed because your colleague asked the question. Double Q learning for fighting the maximization bias. If you remember 2 lectures ago, we discussed exactly about this problem, and we showed this picture where there are 2 states, A and B, and from B onwards, there are multiple actions whose mean rewards are sampled from that Gaussian, whose has a mean of minus 0.1. And we discussed the problem with taking the argmax under a Q, estimated Q, and then evaluating that argmax under the same Q. And we talked about the maximization bias. So the same maximization bias holds here in deep Q learning, all right? So the same way we had tabular Q learning, now we have double deep Q learning, which is the following. We're going to use different W's to estimate the argmax and to evaluate the argmax. And guess what? We may as well use the W and W minus, since these are the 2 functions hanging around. Now, if you want, you can also use another one. Okay. And so we have action selection, essentially argmax based on W, and evaluation based on W minus, essentially. All right. And here is another solution from that famous paper, Fujimoto et al. 2018, which has another even more aggressive, handling of that maximization bias by taking the minimum across the 2 W's, W or W minus. Okay. So instead of taking the argmax under one and evaluating under the other, it takes the argmax under one and it takes the minimum across the two. All right. Make sure that it's as pessimistic as possible. Okay. In case you want to check that. Yeah, here is the prioritized experience replay, which your colleague mentioned. We store experience tuples using a priority queue according to the DQN error. And the DQN error is the difference between what your current network W estimates for a particular state and action and the target, right? The Q learning target. Immediate reward plus gamma max across future actions of the Q S prime A prime W minus. All right. High error, high priority. You need to play that tuple a lot. If that error is 0, even if you sample that tuple and feed it in your network, it's not going to update your parameters. It's a useless tuple to play in your batch. Does this make sense? This is a standard thing that we do also for supervised learning. We call it maybe hard negative mining. So we have examples, we compute the error, and then we sample those more often, all right? As opposed to examples that have 0 error. And you know what? When this error is 0, the gradient updates are also 0. They have 0 effect into our parameters. Is that clear? Okay. So PI, essentially the priority is proportional to the DQN error. Yeah, and if A is 0, we have the uniform samples. Here is another very, very, very simple extension. In fact, we had discussed it already. And it's called the N-step multi-step Q learning update rule. So far, we have seen Monte Carlo NTD being very, very different than one another. All right. One bootstraps, the other doesn't, and so on and so forth. Well, guess what? Instead of just using the immediate reward of the first time step, you can actually use, let me show you, the reward of multiple N time steps. And it looks like this. This is how it looks like. So for this is a 2 time step. Let me show. Yeah, and this is the general N step time step, which means what? I pick N, let's say N equals 5, and then I form my targets as follows. I take immediate discounted rewards. Capital R is exactly the rewards that show up in my trajectories. Okay, I multiply with the gamma appropriately, and then I go to the N plus 1 step, and there I use the V or Q of the next, the V or Q estimate. Does this make sense? So instead of taking immediate reward plus gamma, V or Q of the next state and action, I can take immediate rewards appropriately discounted for a number of steps plus gamma to the appropriate power of my estimate or V or Q of the next match next state and action. Is that clear? And as you see, there is now a continuum between GT 0, all right? 0 or yes, GT 0, which is what we've seen so far, and GT infinity, which is Monte Carlo, right? And only the immediate rewards show up along the trajectory and never an estimate of the value, a capital V or capital Q. So it looks something like this. So we have 1 step TD or 2 step or 3 step and so on. So there is a continuum between, short and thin updates and long and thin updates of Monte Carlo. Very straightforward, right? Any questions here? In fact, in the next lecture, when we talk about policy gradients, we're going to see a method that uses N equals 5. Yeah, actually, I have a picture here to show you how exactly it's going to happen. So now you want to compute no value update. Yeah. So essentially, so here's how it happens. Trajectories come and you want to apply your N-step rule. And in the beginning, in the first state, when you have not seen enough immediate steps, when you have set N equals 5, and you haven't seen yet 5 steps of the trajectory, then you cannot do any updates, right? Because your equation, your target involves 5 immediate rewards, right? So you need to wait till you see 5 immediate rewards. And then, so this is where we call end step TD. From here to here, then yes, you'll use your, end steps plus, estimates of the next time step. And here towards the end of the trajectory, we're just going to use this Monte Carlo, all right? Because the value estimate essentially is of the future state and the trajectory terminated earlier than that. Is that clear? In practice, that's how it works, okay? Okay. So basically, the states towards the end of the trajectory, you just form MC targets for them. Okay, that's it. And if you are curious to know how the, expected SARSA, how it looks like, the target, if you remember there, we had a summation over all possible actions, each one multiplied with the probability of that action, which we know because we know the policy that we're using. And we said that this target essentially is more computationally expensive than SARSA. And, people, I haven't seen it a lot in papers, and I'm not exactly sure you need to worry that much about it, all right? But in any case, now you know how to generalize from TD0 to TDN and so on. So conclusions regarding end-step methods, they generalize TD and Monte Carlo, okay? And we slide from the one to the other as n increases from TD to MC, okay? N equals 1 is TD, n equals infinity is Monte Carlo, and an intermediate n is much better than either extreme. It can be applied to both continuous and episodic problems, and so on and so forth. Yeah, that's it. So that was very easy. And then now we're going to jump to something that's slightly more, requires more our attention. Okay, now we require more than attention. And this is this paper. So now we're trying to think the difference between the reinforcement learning method that we just saw, deep Q learning, okay, and planning with Monte Carlo tree search. Now, before we jump to that comparison, does anybody have any questions? We don't have any questions. Okay, so let's see. So this is also one of the required readings, and we usually ask questions from that paper in the quiz, guys. Okay, so here is what this paper suggests. It says we are going to learn to play Atari games in real time, but we're going to use offline Monte Carlo tree search planning. That's what it says. Okay, so the truth is that we know how the Atari environment works. We know the simulator, all right? So, and because exactly we know the simulator and we know which states transition to which states, we can use Monte Carlo tree search to just search the environment and compute queues for state and actions. Let's just try to understand one more time, remind ourselves what Monte Carlo tree search does. It selects a particular state, it puts in mind a particular state, and then for all the actions that are children from that particular state, all the 18 actions here in Atari games, will compute a particular queue. Do you remember that, guys? And how do you compute that queue? Well, by sampling trajectories. In fact, I have some pictures here to remind you how exactly it works. So what this paper is suggesting is the following. Forget about deep Q learning. Just run Monte Carlo tree search planner and sample states, and then run tons of trajectories, compute the queues for the state and for that state and different actions, and use those as the targets for what? For training a Q network. So instead of using MC targets, or instead of using TD targets or TD0, TDN, and so on, whatever we said, he said, throw those away. These are too noisy. Okay? Form awesome targets by running a planning procedure. And the question is, will the Q value function you're going to learn in this way, supervised by the planner, will it be better or worse than the one you're going to learn using reinforcement learning? This is what the paper is about. Now let's take it step by step. Well, they say the following. They say, don't worry that the planning is very slow. That's another thing they're thinking about. Why we use planning methods to play chess and not to play Atari? Well, in Atari, you need to play really fast. You don't have time to think and do 3 searches and so on. Is really, really fast playing. Do you see that thing, guys? That's why they're saying, we're going to do planning offline just to compute Q values, and then we're going to learn deep networks to distill those Q values into a function, Q, which we're going to use to play the game. What means to play the game? At every state, I feed the state, I spit out the 18 values for the probabilities of different actions, and I just sample from that policy. Is that clear? So then I'm very, very fast at test time. Now, training time, I'm very, very, very slow because 3 search takes very long time. Is that clear? Okay, let me remind you how Monte Carlo tree search works. So their idea is the following. We're going to have a Monte Carlo tree search agent that plans against itself and generates tuples of the form state action and the correct Q value. All right. So this should not be super essentially unintuitive. It's a competition between the Monte Carlo tree search targets, those Qs that you see, and these targets that we used earlier from the trajectories of the agent. And then they say, once I collect this huge data set for my planning process, I'm going to use it to train 2 agents. The first is I'm going to train a regression, okay, that given a state and action regresses to the corresponding Q of the particular action. And then I will select actions using the argmax of that Q. The second is I'm going to train a classifier that essentially given 4 frames as input, much like the deep QN. You remember the 4 frames were always concatenated and fit into that Q function, just predicts the best out of the 18 actions. All right. So either I'm going to train a regression network or a classification networks. And can we use the learned policies to play the game? Yes, we can, right? Then we're going to be sampling actions either from our regression network or from our classifier. That is their suggestion. That's what they're suggesting in the paper. And then we're going to go now into details. Are there any questions into their suggestions? Okay, so let me then remind you what Monte Carlo research is, and maybe you have questions afterwards, all right? So Monte Carlo does the following. It iterates between the following stages. It selects actions within what we call the tree using the UCB criterion. Once it reaches to the frontier, it expands. It selects a new node, and essentially it's expanded by 1 node, 1 state per rollout, per trajectory. After it reaches the frontier, it just plays randomly till the end of the game, okay? Just play randomly, see if you win or lose, and then back propagate the values, which means what? Once you reach the terminal node, go and update the value estimates as well as the NT of A, how many times an action has been selected, in all state and actions that you took while going from the root all the way to the end of the game. Do you remember this, guys? Okay. So the UCB criterion, you remember it? I mean, I think you do. Now, the best way is to see the picture here. The UCB, just to remind you a little bit, is essentially we have a summation, we have an exploration bonus, and a Q estimate, and we want at every state to sample actions that have high Q, but also have not been trying a lot. All right? Does this make sense? So the NT of that alpha needs to be small, okay? So we put in our head a particular root node, so we just sample a state, and then we just start playing the game. And here, essentially, we use the UCB because we're within the tree, and we select actions, all right? And then we reach the end of the tree, we attach a new node in the tree, then we play randomly, then we go till the end, oh, we lost. Well, if you lost, then you need to go in all actions that you took along your path and essentially make their Qs a little bit lower. That's all. Does this make sense? And then you repeat and repeat and repeat. And for the same route, you use tons and tons and tons of different rollouts, different trajectories that go from that route all the way till the end of the game. Is this clear? Yes.
First line says if all children expanded, then we do a UCB plan.
Yeah.
Does this mean we've seen at least one rollout from all of the children?
Yeah, right. So this is just a detail, guys. So the following is the following. Because the UCB criterion, if you remember, has NT of alpha on the denominator, which is how many times you have selected a particular action. If that number of actions is 0, then that blows up, which means for every state, first you need to play every of the 18 actions. So you'll collect 18 trajectories, all right, coming out. Once you do that, then you start playing based on the UCB. You don't need to select each one. You look at their UCB values, okay, and you take the argmax, okay. That's all. And by the way, that also is going to show up in the homework. The Monte Carlo tree search, you will need to code up such a thing. So it's good to ask questions now if they come up. Now, because I know that we made a mistake and we didn't put the subchapter, probably you haven't read it, so that's fine. You can ask questions next time. That's all right, okay. We can still discuss. So my question for you guys is the following. I have that planner, and that planner for a particular root state, I can do thousands and thousands of rollouts and compute some Q estimates for the children actions of that state. All the 18 different actions that come below that root, right? Do you agree that that's going to be the output of that planning procedure? Q estimates for the actions of the root? Now, my question is, are these good Q estimates, or you think the estimates that we had in our DQN was better? Like, oh, immediate reward plus gamma Q of the next state and so on. That's my question, because that's what these authors suggest. These authors suggest I'll use my Monte Carlo planner to essentially form Q estimates to train a Q value function. That's what it says. Okay, so let's ask the questions because we only have 2 minutes. Which one, in your opinion, Monte Carlo tree search or DQN procedure, discovers better action? That is, better Q estimates. That if we agree with respect to them, we achieve higher returns on expectation. What do you guys think? Yes.
Monte Carlo, because it more explicitly chooses random actions at any new state or new situation.
I think maybe you're saying Monte Carlo search because it more methodically searches the state space as opposed to, okay, let me sample a trajectory. Is this what you're saying? Okay. Other people? Yes?
Yeah, I think it's MCTS also for that reason, but also because the estimates are with TQN, our target estimates were always biased by the error that we're currently making because we're using the current network to set it out. But in MCTS, we're just looking at, okay, this is what it's supposed to do.
Right. So what you're saying is that if we were using Monte Carlo estimates that are unbiased, then we were doing better, you think, or because we can use Monte Carlo estimates if you like. If this is your problem that our targets are immediate reward plus gamma and value of the next state, I can be setting my targets based on Monte Carlo returns. Do you see that are unbiased? Yes.
You have a very large state space. Monte Carlo might take a long time to converge, whereas the network might approximately very quickly.
So now your colleague brought a very important aspect. He says depends on the resources. The planning procedure to get good Q estimates requires some time to search. Correct? Good question. Good point. Other points? Yes.
Would it depend on the context? Like I know in the original like teacher that started to do it, you know, these like non-cultures, we get them like to see the common spot compared to like
I didn't hear what you said. It depends on the context, and then I didn't hear what you said.
Oh, sorry. So like in the first design paper, I know you use yeah. They use the DQN because I guess like the game is very it's not like home based, it's something like but then like and obviously we trained offline before
Right, that's true. I mean, this is what they did, but now we're trying to decide why. why it is useful to do the planner and under what conditions, right? Okay, so if there are no other comments, I think what your colleague put down is very important. It depends on the compute. I mean, I can give you very tiny compute for your planner, and I'm pretty sure your Q estimates are going to be super crappy. Okay. However, with a lot of, if I give you a lot, allocate you a lot of time, the planner will do better, more exhaustive search of the state space because it keeps track of what have I visited, where I am right now. I keep the Q, I take into account intelligent exploration, not epsilon greedy, and my Q targets are very, very, very informed compared to, oh, here is a random trajectory, here is the sum of rewards, and so on and so forth. Okay, so you will see that those Q targets are more informed, even if you blow up the DQN more, let's say. Okay, and we say why we don't use MCTS to select actions if the Qs are so great? Well, because the planner is terribly, terribly slow. So it can only be useful offline at this stage, at least. That this is a very elementary planner. We haven't, boosted up the planner with deep nets and so on yet, which we're going to do in a future lecture. And how can we use both the good estimates of CTS and play fast? Well, we distill them in a policy. Okay. And to be honest, because it's 112 and this is insanely important, I will continue on Wednesday. It would be, of course, super great if you can read that paper. This is one of the very, very good papers of the course. All right. So see you on Wednesday.